Good morning. Today's class I will be discussing the concept of discontinuity of a function. Continuous function we have learned a lot. You know, under what condition a function is continuous at a point. A function is said to be continuous at a point if left hand limit, better to say if limit extending to a fx equals with f. Or you can write for by considering existence of limit, that limit extending to a minus fx equal to limit extending to a plus fx, that is equal to fa. If it happens, then the function is said to be continuous. But if either this not equal to this or this not equal to this, any one of these two equalities not satisfied, then the function will be discontinuous over there. But when you say function discontinuous, then situation may arise this manner. These two are not equal. Limit is not existing. Or it may happen that the limiting value of both the limits coming infinity, minus infinity, or some undefined quantity. Or it may happen in such a manner that they exist but they are not equal. Or it may happen that the denominator is always equal to 0 at the specified point. All these cases we are going to discuss one by one. First, we will discuss discontinuity of first kind and second kind. Discontinuity of first kind means here the limit extending to a minus, a plus all exist, even fa also exists, but you will see that the condition of continuity is not satisfied. In discontinuity of first kind, all these three may exist, but condition of continuity is not satisfied. In second kind, what will happen? In discontinuity of second kind, you will find that either one of the limit or both the limits are coming infinity or they are undefined over there. We are going to discuss continuity of first kind first. What do you see in discontinuity of first kind? In discontinuity of first kind, at a point x equal to a, the limit x tending to a minus fx and limit x tending to a plus fx exist, but the condition of continuity is not satisfied here. Okay, if you observe this function, then what is the value of limit extending to 3fx? This is the graph of function. Obviously it is discontinuous. Limit extending to 3 minus fx, you can see the value is equal to, it corresponds with, suppose it is corresponding with 1.8. So its value, this is say 1.8, we will write this value is 1.8, but limit extending to 3 plus fx is going to be what? This will be, this has value, you can see that limit extends to 3 plus corresponding with 4. Okay, this is corresponding with 4, so they are not equal. Condition of continuity is not satisfied. It is obviously continuity of first kind. Similarly, you can consider this function fx equal to mod of x by x for x not equal to 0 and 1 for x equal to 0. If you rewrite the value, if you rewrite mod x here, that fx can be written as x by x for x greater than 0. This will be minus x by x for x less than 0 and 1 for x equal to 0. So fx is going to be 1 for x greater than 0, minus 1 for x less than 0, equal to 0 for x equal to 0. If you calculate the value of the limit x tending to 1 minus fx, what do you observe? This sorry, not 1 minus, it is 0 minus. At the point 0 you will check, this is coming minus 1. Limit x tending to 0 plus happening what? This is going to be equal to plus 1. So the condition of existence of limit is not satisfied. Continuity condition is not satisfied. So the function is discontinuous, and it is discontinuity of first kind. So what is discontinuity of second kind? This I am going to explain. In case of discontinuity of second kind, either one of the limit or both the limits are equal to plus infinity or minus infinity, or they don't exist. If one of the limit, suppose this is the point A, in this function what do you observe? If we calculate limit x tending to a plus, the value of fx is infinity. If you calculate limit x tending to a minus fx, this is going to be minus infinity. Okay, so this is discontinuity of second kind. And discontinuity of second kind, it may happen that limit is not existing over there. This is one of the cases where limit doesn't exist, and infinity is an undefined quantity. That way also you can say it is a discontinuous function, but this time it is discontinuity of second kind. So in discontinuity of second kind, one of the limit or both the limits must be infinity or minus infinity, or they don't exist at all. Let me take one example here, another example, that say we are going to find continuity of this thing, that fx equal to 1 by say 7 minus x at x equal to 7. Does it have discontinuity of second kind? Let us check. Limit x tending to 7 minus fx. What do you observe there? It is going to be 7 minus is a quantity which is smaller than 7. So from 7 if you subtract, you will get plus 0 over there, 1 by 0. So this is infinity. And if you calculate limit x tending to 7 plus fx, what do you observe? This is going to be 7 minus 7 plus. 7 plus is a quantity which is larger than 1. So when subtracted from 7, you will be getting minus 0. So the answer is minus infinity. Okay. So this function fx equal to 7 minus x has discontinuity of second kind at x equal to 7. Alright. So I am going to explain what is the concept of piecewise continuous function. The function arises in the form of two or more pieces. Okay. Those pieces are continuous in the interval where they lie separately, but at the point where the function nature is going to be changed, I mean one polynomial to another polynomial, one first degree to one second degree, or first degree to another type of first degree polynomial, at those points it may not be continuous, but it is continuous at all every other point. I have taken two examples here. You can see it is piecewise continuous beyond this point 1. It is piecewise continuous from, say, this is 1 2 3 4, minus 4 to 1, no 1, just minus 4 to 1 open interval. It is piecewise continuous before the point minus 4, but it is not continuous at the points where there is a change in the function. It means one polynomial to another polynomial function is going to be changed. This is said to be piecewise continuous, as if those pieces are continuous, but the point where there is a jump, the function will not be continuous over there. Okay, so piecewise continuous function is a characteristic of discontinuity of first kind. It happens in case of discontinuity of first kind. We never say it is possible in case of discontinuity of second kind. It is possible for discontinuity of first kind only. Okay. Question will arise here. The question is whether continuity can be removed or not. You must be very clear about existence of limit. If limit doesn't exist, then you can never say that it is continuous. But suppose a function given this way, that fx equal to, let me define the function first, 2x plus 3 when x greater than 1, this is 3x plus 2 when x less than 1, and this is 10 when x equal to 1. Okay, here limit x tending to 1 plus fx going to be what? 2 into 1 plus 3, that is 5. Limit x tending to 1 minus fx going to be what? 3 into 2 plus 1, 3 into 1 plus 2, that is also 5. And f1, that is 10. So here limit exists but not equal to functional value. Okay. But here if we change this condition, if we say that no, we will redefine the function by writing f1 equal to 5, then the function become continuous. Okay. So in this case, that is referred as continuous extension of a function. But this time I am going to explain what is isolated point discontinuity here and what is missing point discontinuity. This is the kind of isolated point discontinuity, and missing point discontinuity will be what? Something like this. Say fx equal to x square minus 9 by x minus 3. Only this problem is given. Okay. So this function has missing point discontinuity at x equal to 3. Why? If you find limit x tending to 3, x square minus 9 by x minus 3, this is going to be extending to 3, x plus 3, x minus 3 by x minus 3. Okay, you cancel these two factors. X not equal to 3, you write the value going to be 3 plus 3 equal to 6. But for continuity, you need to find f3. What is f3 here? F3 we don't know. But if somebody says that no, I am redefining, I am writing f3 equal to 6, then the discontinuity can be removed. This is called missing point discontinuity. Okay. So here I am going to explain details of this kind of discontinuity, which is referred as missing point discontinuity. Missing point, from the definition only it is very clear, something is missing over there. In the definition of this function, which I have taken in the previous case also, the same function I have copied here. In this case, you can see something is missing over there. What? Nothing is told about f3 and nothing told whether this is valid for x equal to 3 or not. This kind of discontinuity is called missing point discontinuity. If you check limit x tending to 3 minus fx, or limit extending to 3 plus fx, or limit x tending to 3fx, then in all cases value is the same. What is the value here? You need not calculate left hand limit, right hand limit separately. You just find x plus 3, x minus 3, this by x minus 3. The factor get cancelled. You will write since x not equal to 3. So this is coming to be 3 plus 3, that is equal to 6. If somebody says that, okay, that missing point, I'll fill it up. How? I'll be writing in case of f3 equal to 6. Then it is okay. if we redefine the function this manner, x square minus 9 by x minus 3, when x not equal to 3, and then I add this part for x equal to 3, then it is obviously continuous at x equal to 3. So this missing point discontinuity, actually removable discontinuity, we can remove the discontinuity from here by redefining the function. You must be very clear about it. What happens in isolated point discontinuity? The limit exists, but functional value given over there, but the problem is limiting value is not equal to the functional value. So if you go for calculating here for this problem, limit extending to 0 minus or 0 plus, this is going to be x tending to 0, 1 minus cos 2x by x square, 2 sin square x by x square, 2 will come outside, and this by little bit manipulation I can take limit inside, making square of it. The value is 2 into 1 square, that is 2. Okay, so limit extending to 0 fx is 2, but what is f0 here? F0 is 5. Extending to 0 fx is 2, but f0 is 5. So limit exists but not equal to functional value. This is said to be isolated point discontinuity. Point is isolated. Isolated from where? Isolated from its limit. Limit at one value, functional value at another value exists. So this kind of discontinuity is called isolated point discontinuity, and this is also removable. Why? It becomes, if you redefine the function fx equal to 1 minus cos 2x by x square, x not equal to 0, and this is equal to 5. For x equal to 0, this function is continuous. This function is continuous at x equal to 0. But initially, if they have stated the function this manner, it is not continuous, because functional value not equal to limiting value. We made it continuous. Then when you do this manner, this is referred as continuous extension of a discontinuous function. Function was discontinuous, but we made it continuous forcefully by changing one condition over there. Sorry, this is not 5. This is not 5. I did a mistake over there. This should be equal to 2. If you write 5, then it remains the same. If you write 2, then limiting value equal to functional value. It will be continuous over there. Alright. This I have already explained for this continuous extension of function. Just I will be taking more example to explain. We have discussed removable discontinuity. Let me take one example from removable discontinuity of first kind. Okay, suppose the function fx is given as sine, say 3x by 5x. Okay, this is removable discontinuity. Better to say that is missing point discontinuity. Function is given this way, just the question given this way, discuss continuity here, no other condition given. Okay, this has then removable discontinuity if we can define the function for equal to 0, because if you calculate limit x tending to 0 fx here, the function was only given this manner. They have asked you to check the continuity. Limit x tending to 0 fx is going to be what? Limit x tending to 0 sine 3x by 5x, that is limit x tending to 0 sine 3x by 3x into 3 by 5 3 by 5 will come out, limit extending to 0, sine 3x by 3x, value is going to be equal to 1, so it is 3 by 5. But if somebody says that now to make it continuous, this was not continuous initially, isn't it? It was not continuous initially. We try to make it continuous. This has missing point. It has, better you write this manner, it has missing point discontinuity. Which one is missing here? That x equal to 0, it is not stated. But if we write its continuous extension, to make its continuous function, continuous extension of the above function, this is going to be equal to fx sine 3x by 5x. You write x not equal to 0 equal to 3 by 5 for x equal to 0. Then it's done. This function, it has missing point discontinuity, but this function is, the function is continuous now. Okay, so this was removable discontinuity. We have removed the discontinuity here, and then we have redefined the function for its continuous extension. All right, now let us take another example where I'll be taking isolated point discontinuity. This was example 1. Example 2 you take, it is isolated point discontinuity. Just one more example to clear the concept for you. It is, say, 4 minus x square by 2 minus x, x not equal to 0, equal to 8 for x equal to 0. Here if you calculate, sorry, you take the point 2 here, x not equal to 2 and this is equal to 2. If you calculate limit extending to 2 fx, this is going to be limit 2 plus x, 2 minus x divided by 2 minus x. So you cancel the factor, it's coming to be 2 plus 2, 4. And f2 is what? That is 8. They are not equal. So this function is said to have isolated point discontinuity. The function has isolated point discontinuity. To make it continuous, what will be its continuous extension? Continuous extension going to be fx equal to 4 minus x square by 2 minus x, x not equal to 2, and this you write 4 for x equal to 2. Then it will be continuous extension of a discontinuous function as it has discontinuity of, as it has removable discontinuity. You must listen to me carefully for continuity of function. So far we have seen that the limits should exist. If limit doesn't exist, then you can never make it continuous. In case of removable discontinuity, we have seen that continuity can be removed if limit exists, but that is not equal to functional value or functional value not given at all. But here, in irremovable discontinuity, you can never remove discontinuity here. Why? Because for this function at x equal to a, you can say that before a it is going to be plus infinity, after a it is going to be minus infinity. It is infinite discontinuity, two limits are different. Here, this is one that at the point a extending to a plus, the value is something like minus k, and here a minus, it is something like plus k. So you can never make it continuous. At this point x equal to a value is oscillating very fast. Just after a, one value of the limit, before a, another value of limit. Here also you cannot make the function continuous. So these three functions, all three shown in the diagram, have irremovable discontinuity. In the first case, it is said to be infinite discontinuity. You can never remove discontinuity here. Jump discontinuity, limit exists but they are not equal. So this jump discontinuity, you can say that it belongs to the first kind of discontinuity. Yes, of course, the limit exists. Functional value was not equal to that. So jump discontinuity and discontinuity of first kind, similar. Oscillating discontinuity means here, what happens there? There, the value of limit or the functional value oscillate. You cannot say the value properly. Okay, then it is said to be oscillating discontinuity, and you can never remove the discontinuity of this kind. That's why they are called irremovable discontinuity. The kind of irremovable discontinuity I'm going to discuss now is known as jump discontinuity. Here function has a jump. What kind of jump is there? Just before a, suppose the value is k. After the point a, it has value say 3k by 2, but this is going to be negative, so the function has a jump over there. One can say that here if a minus value is k, if a plus has value equal to minus 3k by 2. So the jump of there is a jump of the function, and jump is defined as if a plus difference if a minus. This is the jump. So what kind of jump is there? What is the value of jump here? Jump is given by k plus 3k by 2. This is nothing but 5k by 2. What is the jump for this function? This function, you can say that this you can define. Obviously, this is a straight line and this one is a parabola whose equation can be given nicely. But here, if you see that limit extending to 1 minus, it has a value 1, and fx, and limit extending to 1 plus fx, it has value equal to minus 2. So here also there is a jump, and that jump is given by 1 minus minus 2. This is equal to 0. Okay. So this function discontinuity cannot be removed. You can say that this belongs to first kind of discontinuity. There is a jump existing over there, but limits exist. Two limits exist separately, but they are not equal. That's why saying that limit doesn't exist here. Okay. So this is a jump discontinuity, and the jump of the discontinuity is different. I am going to explain now infinite discontinuity. What is that? This is also discontinuity of that kind where it is irremovable. We cannot remove the discontinuity here because the value of limit extending to a minus going to be minus infinity, limit extending to a plus going to be equal to this one going to be plus infinity. If a minus is plus infinity, a minus, and a plus, it is going to be minus infinity. So this function is infinite discontinuity. We cannot remove the discontinuity here. So this is a kind of irremovable discontinuity. Okay, and irremovable discontinuity will be related to pole. Like this function fx equal to 1 by say x minus 10. It has pole at x equal to 10. Limit x tending to 10 minus, if you calculate, it is going to be equal to 1 by minus 0, value is minus infinity, and limit x tending to 10 plus, this is 1 by 0, that is equal to plus infinity. So this function graph also you can plot easily. This function is a pole at x equal to 10, and the function is said to be infinite discontinuity because value is coming minus infinity, plus infinity, like that. Okay. Pole discontinuity is very much related to infinite discontinuity. A function fx is said to have a pole if we can say that 1 by fx, limit extending to a, 1 by fx is equal to 0. A function fx is said to have a pole at x equal to a if this condition is valid. For this function 1 by x plus 2 by x minus 1, this is going to be x minus 1, x minus 4 by x plus 2. When you compare these two equal to 0, we are getting x equal to 1 and 4. So this function has two poles here. Function, it has poles x equal to 1 and x equal to 4. Okay. So this pole discontinuity related to infinite limit, which we have just discussed. If you find limit x tending to 1 minus fx, you can check 1 minus means it is going to be 1 by 0. I mean minus that if you put, it is coming 3 by minus 0 into, this is going to be 1 minus 4. This is minus 3, something like this. This is going to be infinite. And limit x tending to 1 plus fx, if you find, this is going to be 3 by minus 0, this is minus infinite. Okay, so at 1 it has infinite limit, similarly at equal to 4 it has infinite limit. Function is said to have pole discontinuity or infinite discontinuity at x equal to 1 and x equal to oscillating discontinuity at a point if at least one of the left hand sided limit does not exist because of too much oscillation. But here, too much oscillation on both sides of the point A. This is said to have oscillating discontinuity. The best example, you can take fx equal to sine 1 by x. This has oscillating discontinuity. Why? For this function, if you calculate limit x tending to 0, if you plot the graph, then only it will be quite obvious. Too much oscillation. I cannot draw so many oscillations. I am trying to give you inaccurate one. Mine is already in. See, about the point 0, there will be many oscillations for sine 1 by x. So this is said to have oscillatory discontinuity, and by redefining the function, you cannot remove discontinuity here also. Okay, that's why it is called oscillatory discontinuity.